question would be, why should we do, or why should I be interested in doing geomorphology? The things that drive my research are basically these two topics depicted above, which is we are confronted in the next, well, hopefully not centuries, but at least the next decades, with increasing natural hazards and also with the phenomenon of dwindling resources, right? That basically means that the natural hazards could be driven by slope processes, gravitation, but they could also be driven by fluvial hazards, like depicted here in this flood, which hit this little alpine village. But you could basically scale that, right, from little villages to large cities that are becoming inundated. And the dwindling resources basically tackle everything in terms of groundwater, open water bodies at the Earth's surface, but also the loss of soil and in some way also the loss of sediment. Why do I also do research? Because I just try to avoid situations as depicted in the bottom left picture, which is a picture from Potsdam, basically. So a well-organized city, as you would say, in Germany, a well-behaved city, but sometimes something weird happens, right? It rains a lot and it rains too much in a way that people are simply unprepared, and pavements and streets simply turn into ponds that are so deep that you can take your stand-up paddle and roam around in bits and pieces of Potsdam, basically. Yeah, so one of the things that drives my research is to mitigate that state when we have to say it's too wet and we are too unprepared. On the other hand, that's on the bottom center picture being depicted. This is a vineyard in southern France, right? So one of the home cities or the home regions of growing wine for centuries. And for there, it's simply becoming too hot and too dry to sustain these grape vineyards in the end. And another region where we should and basically have to focus on in the next decades will be depicted in the bottom right part, which is an example of tropical rainforests in the tropics, basically, all around the planet, where it simply gets too hot and too wet. What does that mean? It becomes physically uninhabitable regions because you can sweat as much as you want, because at 100% relative moisture in the air, your sweating doesn't help you to cool down your temperature. And if it gets 100% wet, plus more than 41 degrees Celsius, you will simply not survive in these environments. And this is stuff that we are facing, right? This is environmental change we face right now, and which is projected to happen in the next decades. And this should be one of the things that drives our research. Speaking a bit more directly about the processes and the phenomena which I'm engaged with and which I really like to engage with in future is depicted here. So the top left picture shows situations that kind of frequently happen in active mountain belts. This is a picture from Taiwan, and you can see a street or a road, and you can see a rockfall happening. This is just taken out of a video, and to make sure the car driver survives easily because the block tips to the right. But that is some of these encounters where geomorphology should help and should give advice how to mitigate this, how to understand why these processes happen, when they happen, and how they happen. The same thing happens for basically engineered landscapes like this picture showing here from the Bingham copper mine, which experienced a catastrophic failure. Millions of cubic meters of material moved down, and it was just good luck that nobody was in that pit at the time. It could also be investigations about these glacial lake outburst floods, or simply floods that hit valleys more or less unpredictably. And you can see this 5 to 4 story high house over here. So just to give you some estimate of scale, and you can see from the scouring of these valley floors and the valley itself, how magnificent and how huge this flood must have been that happened in Nepal a couple of years ago. And it could also be man-made disasters, which is depicted down here. That's an almost failed dam that would have caused a massive disaster, actually. But they basically managed to drain this hydropower project before it failed. And there's also seismic investigations related to that. And in the end, it could also be large-scale debris flows, and it can be little flashy rivers that also affect how humans use a landscape and how humans are affected by landscape processes. So this is more or less the realm in which my research is settled. I have to do it like that. And why do I work on that, or how do I work on that? I guess, when you speak about the term waves, you think about something which is depicted in that video, right? Things that open water bodies do. But you can also find waves traveling through media in these semi-liquid media, right? That could be, in this case, this little animal. And obviously, waves can also travel through rigid rock, right? As this is being depicted here in this animation of an earthquake which hit Cuba and which sent out waves that travel across North America. So waves are basically a common phenomenon, right? Also in the air, in liquids and in solid bodies. And seismic waves or waves travel with different velocities that depend a bit on the medium. If a wave, a pressure waves, for example, of a blast or of a bomb explosion, if that travels through the air, it has velocities of roughly 340, 330 meters per second, which means it would take almost 3/4 of an hour to travel across Germany. If that same wave would travel in water, it would be quite a bit more fast, right? Almost 4 times faster, or more than 4 times faster. It would just take 10 minutes to travel all across Germany. And if it would be a seismic wave that travels through rigid granite, it would travel at a speed of 5,000 meters per second or 5 kilometers a second. So a seismic wave across Germany takes about 3 minutes, a bit more because not everything in Germany is granite. But just to give you some estimate of the phenomena of seismic waves and how they travel, at which speed they travel. The next question we should ask is, what types of seismic waves are there basically? What are the material I'm working with and that you might become interested in through this lecture, hopefully? Basically, there's two types of waves. There's waves that travel within media, within rock, for example. These are called body waves. And then there's waves that travel at the interface of a solid medium and the atmosphere, or a solid medium and the ocean. And these are called surface waves. And there's basically the ones that you know from school, hopefully. There's so-called P waves or pressure waves, and these simply travel in the direction, or the deformation of the ground happens in the direction in which the wave travels. And then there's the so-called S waves or shear waves, in where the deformation basically happens perpendicular to the propagation of the wave. Yeah, so these are the typical candidates which you know from basic lectures, from textbooks, probably from school and media. At the surface, there's waves which are called Rayleigh waves, and they do this inundating kind of rolling motion, which you know from ocean waves. And they simply arise from the interference of P waves and S waves as they travel, and they only happen at the surface. And then there's a fourth wave type, which is called love wave, and they are kind of similar to the shear waves, but also only happening at the surface. And if we speak about environmental seismology, then it is basically these two types, right? It's the Rayleigh waves and it's the love waves. So most of the signals we are working with are dominated by surface waves. But how do we actually measure seismic waves? I guess you're familiar with this basic concept of how to build a seismograph. You need a roll of paper, which is rotating. You need an inert mass, which is holding a pen. And as this roll of paper is being shook back and forth, the pen will simply depict this motion. And you can enroll this piece of paper and then interpret this as a time series of ground motion. Well, people also depicted the idea that we can also, instead of papers, use coils, electromagnetic things, and we just use a magnet and a bit of copper wire. And as we move the magnet into and out of the copper wire, we can generate electricity. We can generate a current. And basically, the voltage of this current depends solely on how fast you shake the magnet. So in other words, if you shake the magnet violently, you create a high or large voltage. If you do it subtly or slowly, the voltage which you will generate is, also small. And now all you need to do is basically put the stuff into a proper housing, right? So which is depicted basically here. So you see again, the magnet is simply being shook by the earth back and forth or up and down. And as it does so, it simply moves in and out of this coil and it generates simply electricity. And that's basically what we measure. And that's all of it. That's the principle of building seismometers or geophones, to be specific. And these can be put into these rigid housings, and all you have to do is putting them into the ground or onto the ground. This is a sensor which only records seismic waves that have a vertical component that go up and down. And these sensors also come as so-called three-component sensors. So they sense how the ground shakes in north and south direction, in east and west direction, and also in the vertical direction. And finally, this little cube, which you see on the top left picture, is a data logger or a digitizer. And all that this device does is simply recording the velocity, the voltage which is being generated by the geophone, right? So basically, it's an electromagnet, and you basically measure the velocity, which is indicated by the voltage. That's all you do. That's how a seismometer basically works. A bit more information about that. I mean, I said already, it's voltage proportional to the ground velocity. And the velocity is in really small units. As you can see, we are speaking about micrometers per second, which is 1,000,000 times slower than you would typically walk through the city. Yeah. So these are really tiny signals in the end. And the frequencies with which the ground basically shakes is, at least for the environmental seismology case, is between 1 hertz or one oscillation per second up to roughly about 100 hertz. So that's basically, you start at your heartbeat rate, about 60 beats per minute. This is one of the general signals of seismic sources in environmental conditions. And from about 16 to 18 hertz, you can basically start to hear these vibrations. Yeah, so this is the frequency range we are working in. We do these measurements of the ground velocity at really high resolution. We do this at 200 measurements per second, which means in the end, we end up after 1 year of continuous recording with about 6.3 billion samples. So that means we deal with a lot of data. And the interesting part will then basically be depicted in the last line. It is the search for the needle in a haystack, right? We are looking for really brief events. If you think about rockfalls, which last a couple of seconds or minutes, and you have to screen years or decades of seismic data for them, then it really is boiling down to finding a needle in a haystack. How does a station, or what does a seismic station basically look like? In the easiest way, when you do active seismic surveys, it looks just like that. You depict or you deploy these little yellow sensors, which you might see in this line in the middle ground. And these are the geophones, and the little black cubes are the data loggers, just the ones which I showed you. And you can simply put them into the ground and start recording for active seismic surveys. If you want to do that for a bit more dedicated and long-term deployment, so if you want to record for several months, even up to years, you have to do a bit extra effort, which means you have to dig a hole, you have to dig a pit, and into this pit goes the seismic sensor. In this case, the seismic sensor is this little green coffee mug-like thing which you see in the middle ground, right? Just right of this person who is actually digging. This pale green device, this is a seismic instrument. This goes into the ground about 0.5 meter deep, gets connected through this long black cable, which is visible, to the data logger, which you can see together with an ordinary car battery in this plastic box. And this setup allows you to record seismic data for 3 to 4 months, roughly, independently. And you can even go a bit more advanced, as is being shown here on this alpine peak, which we have sensed a couple of years ago, and build telemetric stations. These are seismic stations which send the data in almost real time to a server, and where you can have a real-time information about what is happening at this peak. And this is one of the key preconditions to move towards early warning, right? You have to have almost real-time access to your data. But basically, this is how what such a seismic station could look like. What about the data? To wrap this up, as I said, we basically record ground velocity as a really high-resolved time series. And this is what we call a seismogram, which is depicted here on the left-hand side. The x-axis is time. In this time, it's it's roughly a day of a storm which hits the little island at the Baltic Sea, basically. And the y-axis is, as I said, ground velocity. And you can see the units are basically 10 to the minus 5 meters per second. So that's about 10 to 20 micrometers per second. Yeah, again, really tiny velocities. And in the end, it looks, well, kind of boring to look at the seismogram, right? It's, as I said, almost a day of subtle ground motion back and forth. And that gives rise to a second way of looking at exactly the same data, and that is we look at the frequency content of the data, right? Not at the absolute values, but at the frequency which builds these seismic data. And how do we do that? We basically cut these continuous seismograms into small windows, 10 seconds long, 20 seconds long. And with each of these little snippets, we do something which is called the Fourier transform. So basically, we express the time series as a linear combination of sine waves, and that allows us to give an estimate of which frequency delivers most of the seismic power to the signal. And that's the way you can do that. You do that, as I said, every 10 to 20 seconds, and then you simply stack these spectral information in time. So this is what is called a spectrogram. Again, on the x-axis, we have time. It's the same time as, or the same time period as on the left-hand side. But now on the y-axis, we have frequency in a logarithmic scale, right? So here we have 0.1 hertz, here we have 1 hertz, here is 10 hertz, and way up here would be 100 hertz. And the temperature of the color gives you some information about the energy at a given time along the x-axis and at a given frequency along the y-axis. And this changes the picture quite dramatically, right? So this boring seismogram from the left-hand side turns into something which can be literally read like a book of activity on this coastal part of Germany. So what do we see? We basically see a long horizontal red to deep red and even grayish signatures, which is depicted here between 0.2 hertz and roughly 2 hertz. Yeah, so this is continuous through time, and it changes a bit in the energy which it delivers. This is basically the seismic signature of the Baltic Sea and the Atlantic. So this is the hum of the ocean. The ocean simply generates a continuous low frequency band between, usually between 0.2 and 0.5 hertz. If we get close to the coast, it goes to higher frequencies. So this is the imprint of a storm which travels all along the Baltic Sea and the Atlantic in this 1 day duration of the storm. What else do we see? If we look at lower frequencies, you can see this part over here. This is happening at the high wind speeds, at the top wind speeds when the storm passed by the coast. And that's basically the seismic signature of waves, of breaking waves hitting the beach. Yeah, and you see that if you go to lower frequencies, we are already at almost minute frequencies. This is the really large breaking waves that hit the cliff and that hit the beach. And if you go to higher frequencies, that's the smaller waves that hit the beach. They happen more often, but they contain less energy. And if you look at higher frequency, you can see also something which really scales with the wind speed that we can see. And this is basically at frequencies between 20 and up to 50, 60 hertz. So you can basically hear that with your ear already. But this is the seismic signature of trees which sway in the wind. So the wind pushes the trees back and forth as it interferes with them. And this ground vibration is simply measured by a seismometer. Yeah, so you can interpret seismograms also as the interaction of vegetation with wind and with the surface. And you can see other stuff in there. You can see these little horizontal line or the stack of horizontal lines here on the 15th of April. And there's another one on the next day around 8 or 9. And this is the signature of a helicopter passing by. So it's the rotating blades rotating with a given frequency that simply excitate the ground. And you can, if you would zoom in, you can really see this Doppler effect, which you know from sirens that approach you and that pass you by. And as the siren approaches you, you have a higher frequency, and as it passes by, the frequency drops. You can see that here a bit more clear. So I depicted a rich collection of the different seismic sources or the different processes which you could basically approach with this technique, deploying seismic instruments across the landscape, and then you can sense all of that. You can see this is this Doppler effect which I showed, right? This is the frequency of the blade of a helicopter that approaches you, and as it passes you by, you see this frequency drop, just as the sound would go down or the tune would go down. Again, this is the signature of trees swaying in winds, and you can see all these wind gusts which deliver a lot of energy. You can also see the imprint of rain. Each raindrop that hits the earth generates a little seismic wave. This picture shows the collapse of the Pietschengalo, which happened a couple of years ago and which released about 4 million cubic meters of rock, killed a couple of climbers, and eventually turned into a debris flow in the Alps. And this generated a seismic wave which traveled all across Europe. So you could sense this alpine rock slide basically up to Scandinavia, which also says if you're looking for really large events, you can use basically seismic networks whose data is available globally and at real time. And people do that. People use seismic instruments for real-time screening for large mass wasting events. You can also go deep back in time, as depicted here in this spectrogram. This is the seismic signature of a landslide that happened in Western Germany in the year of 1980. So that means seismic data is available for more than 40 years now, and you can still harvest this data to look for the kinetics of events that happened a long time ago. You can also look for little bouncing rocks that make it down a slope. Each of these bursts of red energy through time is the impact of a rock as it bounces down the slope. And the rest, I guess, I more or less showed you. That's the stormy coast. This is something I will show you in the last part of the talk. We can sense basically river dynamics if they are covered by ice. And I will spend a little bit more of introduction time on this last bubble over here, which is the GFZ campus seismic signature. When I started at GFZ, I just wanted to test how well the method works, or how the method works at all, if I understand the signals. So I instrumented the campus at GFZ, if you're familiar with that. This is the entrance gate of GFZ. Then you travel this long road all the way across the campus. There's another sensor over here. I'm currently sitting in this office where you can see, if you can see the mouse arrow, this is where I'm actually sitting at the moment, talking to you, speaking to you. And there's another one close to the canteen. So if people walk along this road or go along this road with their bike and car, you could basically sense that. And this is the spectrogram on the right-hand side. Yeah, and you can see two things. You can actually see the daily pattern in that. So that's a Thursday, this is a Friday, then you have the weekend, Saturday and Sunday, and then again Monday, Tuesday, Wednesday, Thursday, Friday, and so on. So you see this, the signature of people actually working on the earth, people that go to work, people that are at work, people that go home. And you can also see the lunch break in there, right? You can see the slight drop in energy during the lunch breaks. What you can also see, if you look closely, you see a horizontal line here around 50 Hertz. This is the ever-present power network in Germany, right? This is simply the 50 Hertz signal within the power lines in Germany. And there's another one here around 22.3 Hertz. This is the power line of the tram and all the trains across Germany. So you will always find these two horizontal lines in many seismograms in Germany and across Europe, obviously. Okay, here it gets more interesting not to look at the spectrogram, but to look at the waveforms or the time series. And as you do that and look at the three stations, each on each other, or for each on each other, you can see you have this consistent appearance of patterns, right? Like here you have first a signal arising on the stations close to the GFZ entrance. And a couple of seconds or minutes later, you can see that it basically appears over here. So obviously this is something going from here to there. And then just a couple of seconds later, you see the same progression of the signal, first at the entrance, then at the GFZ building, and then towards the canteen. And then something bigger, right? But the same progression, entrance, GFZ entrance, canteen. And then you can basically trace that through. You can, in the end, simply convert location and time delay to to velocity. So this is a car which basically goes with almost 40 kilometers an hour out of the GFZ or out of the campus. This is another bicycle, basically, I should say. This is a bicycle coming in. And these large ones are basically trucks or large cars. Yeah, and you can see that officially we have a speed limit of 10 kilometers at the GFZ, and you can see that it's not too many people that basically adhere to that. Sorry, I just had to kill the telephone. And then you can see one of the signatures, which is kind of standing out in the end, right? So you see it at the entrance, and then a long time later, you can see it a couple of hundreds of meters further away. And you can also see that the signal looks different than the signal generated by cars or trucks or bicycles. And it moves basically at about 5.5 meters per second, kilometers per hour, actually, I should say. So this is the speed with which you would be walking across a city, right? That's the typical walking speed. And if you zoom into that, then you can basically see that this is the signature of a person passing by a seismic station. You can see how the amplitude goes up. And this you can see basically for each of the steps, which generates an own seismic signal. And as the person passes by the seismic instrument, the amplitude is highest and then basically falls off as the person moves away. And from this and the difference between the two stations, you can calculate the walking speed. You can say that it's 11 steps in 10 seconds, which means you can determine the step length. And if you take the clever conversion and transfer functions of famous persons in the TV, you can even convert that to body size. So that's what I wanted to express with that. There's a lot of information hidden in these seismic signals, and they simply need to be revealed, and they need to be untouched, or not untouched, they need to be revealed. I should say it like that, right? And people are just starting to do that in very different ways, and I'm hopefully going to show you a couple of examples of that. One more thing, rockfalls in the German flatlands. This is what we did in the last couple of years, simply to go beyond just interpreting the seismic signals like in a qualitative way or descriptive way, but turning these information into kinetic information or into quantitative information about the process. So what we did was going to the flatlands of Germany. That's about 2 hours north of Potsdam, where we have a crane in the middle of a forest, which we could use to drop rocks. And all around this area, we deployed seismic instruments. In the end, about 30 seismic sensors. Each of these little white dots is a sensor. And then we simply dropped the rocks and measured the signals. The rocks were as small as tiny pebbles, which are not depicted here. And the largest one was a 100-kilogram heavy rock, which was also dropped for almost 30 meters. It looked like that, right? So you simply lift it up with the gondola. And in the end, you just released it. And that apparently was a lot of fun to the people involved. And you can even see that as the rock hits the ground, you see the rebound, and we converted this into seismic signals. The idea was of this play to basically be able to also shed some light onto these larger rockfalls, right? Because these are basically something which you cannot predict and which you cannot easily instrument, not as easily as in our experiment. But this is the scale transfer which we are going to implement at the moment. So what does the signal look like? It basically, for the mean example, it's just a single impact, and the frequency which is excited is around 10 to 15 hertz, which is this little bubble down here. And if you increase the size of the rock, the frequency of the seismic signal goes down. In other words, if you have some information on the seismic frequency, you can invert that for the mass, or you can invert that for the volume of rock that has been involved. And the amplitude of the signal can be related to the kinetic energy, hence the drop height or the fall height or the velocity of the rock. And as I said, the seismic waves travel with a given velocity, and from this velocity difference or the time difference with which the signal is being recorded at different stations, at different distances, you can even back project the seismic origin. So the seismic approach, in the end, to wrap this up, gives us the chance to instrument entire catchments, right? For really large events, you can do this globally. Your catchment is the Earth, basically. But you can scale that down to smaller catchments as well. And then you can do that continuously, right? 24/7. For several years, you can record seismic activity due to geomorphic processes. And you can give precise information on the onset of events, on the duration of events. You can give insight into the kinetics, so the evolution of events, and you can even give an estimate of where these processes happen and how they might travel across this catchment. So you get a complete 24/7 estimate on what is happening, when, and where it is happening. So let's now start to exploit this a little bit. For the next couple of minutes, I simply do this in two basic examples, or two main examples. One example is aiming at looking at the history, or at the dynamics that happen in river systems, in floods, and also in terms of sediment transport within river systems. And the other one grades into kind of a complex succession of different hazard events. Okay, if we think about rivers and seismic signals, seismology classically move away from rivers as far as they can, because they know that rivers contaminate the seismic record. Why? Because rivers simply generate seismic waves. And it was just Arnaud Bertin who started that almost 13 years ago, to think the story just the other way around, right? Not thinking of rivers generating noise that contaminates seismic records, but in other ways, using seismic records to infer something about river dynamics. So basically to use seismic sensors to look at systems which are inherently difficult to survey in any other way. And obviously, there is a relation between river discharge and the seismic signal, which is depicted down here. On the x-axis, which is a bit strange, we have the seismic energy, so the color and temperature in the spectrograms, how much energy is being carried by seismic waves. And on the y-axis, we have water level. And it gets clear that if you increase the water level, you will also increase the seismic energy. In other words, you can use seismic energy as a proxy for water level or for discharge. But the story isn't so easy, right? It is not so easy because if you plot these values, as I do now in the top right part, if you plot them explicitly, as Arnaud did, as a function of time, you start with these blue colors, and then you grade from the blue colors basically from early in the year to the peak season. So that's July and June over here, and then you go back at the fall, at the fall time. And then you will see that you just don't get any linear relation anymore. You get this hysteresis, which has been described, which has been argued, which has rarely been measured though, by many scientists in the end. So the idea is in the beginning of the season, you simply start at a higher relationship. You increase water level and you increase seismic energy, but you increase more seismic energy as you move up, ramp up the water level. The idea behind that is it's not just water moving, it's also sediment that's being moved. It's sediment that's being moved by the river. And then at the end of the season, most of the sediment is supposed to be flushed out by the river. And then on the falling limb, it's basically just the water signal and no longer the bedload signal. Yeah, and that already points at the next problem. It's not just water which generates the seismic signal. It is also the sediment that's being transported by the water. Yeah, so it's a mixture of signals. If you look at this in a bit more detail, I take you to Nepal, a study done by us or by Kristen Cook, published 2 years ago, of this glove which hit Nepal, a couple of years ago. And I told you already, I showed this in the beginning. This is a 5 to 4 story high house. And this gives you some estimate on the violence and this magnificent level of the flood. And you can see that boulders of that size, right? Boulders of the size of a house have been moved by this flood. This is the seismic spectrogram of it. Again, x-axis is time, y-axis is frequency, and you can see way before the flood actually arrives, you can see the strong seismic signature of simply this river which is draining this catchment, between 10 and 20 hertz basically. And then as the flood comes in, you can see how basically the energy goes crazy, right? You just raise the energy level by many orders of magnitude in this case. And you can see that it is not just the river anymore with this low frequency part, but that there's also higher frequencies which are involved. And these higher frequencies are due to the bedload which is being carried by the flood. Now, people have started, again, beyond going away from simply interpreting the seismic record qualitatively, they have started to build physically based models to predict the seismic spectrum due to different sources. And one of the first models was developed by Victor Tsai almost 20 years ago now. It feels just like recent, but it's already 9 years ago. That's crazy. So what he did is he crafted a mathematical expression which allows to predict the seismic spectrum. I just go back. So this allows us to predict one of these vertical lines, right? For bedload transport. So all you need to know about the river is its geometry, the width, the height, the gradient. You need to know about the grain size distribution in that river, and you need to know about the grain size flux, plus a few more parameters. And if you know for a given bedload flux, you can basically calculate the seismic spectrum. And that's a huge step forward, right? And then there was another one, a postdoc of Victor Tsai, 2 years later, Florent Gimbert, crafted and contributed a second model. This is a physically based model to predict the seismic spectrum due to turbulence, due to flow. And that means if you know the same stuff about the river as before, except for the bedload flux, but this time you know something about the water level of this river, then you can also predict the seismic spectrum of this river, simply due to water level or to discharge in the end. And now the interesting part would basically be, can we not combine these two models and use them more interestingly in an invert way, right? It's nice to predict the seismic spectrum for some information we have about the river, but the typical use case is just the other way around, right? Usually we don't know how much sediment the river carries because this is something which is inherently difficult to measure. But we want to know how much sediment the river carries, and we also want to know how much water the river discharges. So we could basically use this model in another way. Yeah, we simply ask for a given measured seismic spectrum or spectrogram. Can we not infer what was the seismic, the water level and the bedload flux that basically creates this seismic signature? And for that, we translated these models from the paper version into two R functions. One is called model turbulence, and the other one is called model bedload. And you can see here all the parameters which you have to estimate, or at best you can use field constraints on them. And then you can basically run the function, and it tells you something about the seismic spectrum. Yeah, frequency on the x-axis, seismic power on the y-axis. And then what you could do is simply pre-calculate a lot of random lookup tables. So what we do is we just put random values on water level and random values on sediment flux, and let the functions pre-calculate the resulting combined spectrum. It looks something like this, right? This is an animation for random values of water level H and bedload flux QS. And as you see, as you randomly change these, you will get always different seismic spectra. And then what we can do is simply compare these lookup tables of given spectra to our empirically measured spectrum. Yeah, and then we can simply find the one lookup spectrum which best explains or which best fits our measured data sets. And then by this way, we say to this empirical spectrum, we can fit one of these lookup tables best. And that means in the end, this means we have a water level of 0.5 meters, for example, and a bedload flux of 400 gram per second and meter of the river. So that's interesting. Yeah, that should work. And we tested that basically by using synthetic data. So we created synthetic time series of water level, which is in this case the blue line, constant water level, and we imposed a bedload flux of up to 1 kilogram at a step change. So we had no bedload flux. We go to 1 kilogram for a minute, and then, or for 1 hour, and then we go linearly down, we ramp it down. And for this, we calculate a synthetic spectrogram, and then we basically go the other way around. We use our inverse model and simply use the spectrogram as input and see how well we can basically predict these synthetic time series of water level and bedload flux. And we do that for this case, and we do it for a case where you would say this is really hard to predict and really hard to invert when you have the synchronous development of bedload flux and flood. We do this for a more realistic case, time series 3, when you have the hydrograph peaking or going up and down, and the bedload wave simply travels almost ahead of the hydrograph or of the flood propagation, which is a really realistic case. And then we did this on not just a synthetic data set, but on a real data set in a small river where we could measure the water level and where we could measure in orange the bedload flux. Again, you see the spectra, and then we do the inversion, and the black lines are basically the model solutions. And you can see that in most cases, the black lines basically hit the independent synthetic data sets, right? You get some mismatch over here. If you look at this, you overestimate the water level. Why? Because we enforce that there is bedload flux and water level. And if you don't have any bedload flux, you simply get the model wrong. But we found a solution for that, but we decisively didn't do this in the synthetic data set. And you get another one over here, the step changes in the water level, which means basically your catalog of lookup tables or lookup reference spectra isn't large enough, and you simply get to these coarse step changes. But in principle, the method with synthetic testing works well. Yeah, you can basically take a spectrogram and from this infer bedload flux and water level. Now testing this with real world data. With this, I would like to take you to I would like to take you to Israel, to a dry part of the world, the Negev Desert, where we have one of the longest operating bedload flux and channel observatories operated by people from the Beersheba University. Basically, the essential parts is we have so-called reed-type bedload samplers, which simply collect all the material that's being carried by the river, and which gives us some time-resolved information on how much sediment is traveling and being carried by the flood. and we deploy the seismometer just close to the bank. And then what you have to do is simply wait, like in this case, the PhD student does, until a flood comes. And you can see the flood carries a lot of rubbish with it, but it also carries a lot of bedload sediment. And you can see how dangerous it is to do the ordinary way of sampling sediment, right? If you don't have these bedload samplers, these slot samplers. So this can be really dangerous. This is a small flood. Usually the floods pass the bank, so the water level rises until they overspill the bank. And then it gets really, really dangerous. And this is one of the advantages of the seismic approach. You instrument away from the channel. Let's look at the data. Yeah, this is, as I already said, this is the real world data. This is the independent information on water level, the blue line. Yellow is the bedload flux. And this time it's not a synthetic spectrogram, but this is the empirical one. This is the seismic record that we have created of the flood. And you could see the flood arising. Yeah, so you can basically see the instantaneous rise of power, and it lasts for more than 2 hours. And then you can see this contamination of the spectrogram. These intensive vertical lines. This is simply people walking back and forth, maintaining the station, and that already gives some indication of the weakness of the seismic method. The seismic method is not just sensitive to floods and not just sediment flux and water level, but it basically records everything. It records wind and rain, cars passing by. It records people. It records animals. Yeah, and that's one of the challenges one has to confront it, or one is confronted with when using the method. But on the right-hand side now is the model solution to that. The dashed lines are again the independently constrained water levels and bedload fluxes. And the gray line is basically the water level and the bedload flux as being transferred from the model, or as being inferred from the model. And you can see that this is I would say, a really nice match. Yeah, not so much for the water level, which is, by the way, really difficult to estimate if the entire signal is dominated by bedload flux, as was the case here. But you can see that the different to measure bedload flux is really well depicted. So we are speaking about deviations of less than 1% of the values, of the independently constrained values. So the method actually works. It works with synthetic data, and it works in this controlled case where we have the independent information. So what do? We could now use it in really challenging environments. In this case, we are in northern Sweden, close to Umeå, which on this inset of the map is roughly around here. So we are in the Arctic. And we wanted to know, this is, by the way, a river, the Severan River, which is about 20 meters wide and about a meter deep only, and which obviously freezes in winter. It freezes just at the surface while there's still water flowing underneath it. And the question was, because we are basically blindfolded as geomorphologists, is there any sediment transport in wintertime? Yeah, because usually you can't sample anything in these river systems in wintertime when it's frozen. You can do, and I show you how we do this, but this will be really a lot of effort in the end if you want to do that routinely. So the question here is there any sediment transport in wintertime, and what's the effect of ice breakup in the spring period? So what did we do? First of all, we installed seismic stations, one at 5 meters to the bank, another one at 15 meters, and another one at about 25 meters further away. And there's a fourth one at about 30 meters upstream, so that we have a triangle of information. We also installed, depicted by the yellow and the blue dots, camera traps to give information about the ice surface and the water level at 10 and 15-minute intervals. And during deployment, because we needed some information about the river, how much water is in there, how fast is it flowing, what's the roughness of the bed of the river system, and so on. And for this, colleagues from Finland and also from Sweden assisted us and drilled basically holes through the ice. 11 holes drilled through the ice. And then these holes have been used to lower an ADCP, so a device which allows you to investigate the flow velocity of the river and also the depth of the riverbed, or the flow height, simply to get all the boundary information we need. As I said, this is a really tedious way, and you can't do that at the routinely basis, right? So this is why we want to go to the seismic approach with that. Well, and now let's look at the data sets which come along here. if we go to the left-hand side first, we know about the water level simply because we know about the ice surface plus the thickness of the ice. So we can constrain that well until the ice breakup period in spring. And after the ice breakup period, we can use, which is the black curve shown over here, we can use the water level from the camera images which we have taken. So this is one of the cameras. The other one took a closer view on a staff gauge, so on the water level which we have placed on the bank. And this allowed us to do this also from an optical perspective at 10-minute intervals. So we have a fairly well informed idea on the water level. And the gray curve here simply shows a scaled estimate using the Manning equation and scaling the water level to a bit further downstream from a gauge which has been instrumented. But what about the bedload flux? We basically don't have any chance to constrain the bedload flux, right? This is first of all the way why we pursue the seismic method, to get any information on bedload flux. However, there is a way to do that, which is simply using transfer functions like the one revised from Meyer Peter Müller, which has been published about 15 years ago by Wong and Parker, which gives at least some estimate on the expected bedload flux. So that should be around 0.5 kilogram per second and meter, and that should go up at peak discharge to about 2.5 kilogram per second and meter. This is as best as you can do with the ordinary approaches, right? This is all you can do, basically. Now let's look at the data. This is the spectrogram of the second closest station, and to me this simply looks, well, rich and beautiful in some way. You can tell a lot about the seismic spectrogram. First of all, the time is again the x-axis. We start on the 10th of April and we go until the beginning of June. This is the period we are mostly interested in. Ice breakup is around here in this time of the year. And the y-axis shows again the frequency, which goes in this time up to 200 hertz. So here's around 100 hertz, that's 50 hertz, and so on. And what you can see is basically this one horizontal continuous signal, which dominates all the time, which you can see all the time in the seismic record. That's the signature of the river flowing underneath the ice first and then flowing on the free surface. So obviously we have continuous flow of the water. And if you look at the color of this line as you go through, you can see that it increases with in intensity. You get more seismic power, especially after ice breakup during the spring flood, and then it recedes again as you go towards the summer period. The ice breakup is basically recorded seismically by these strong pulses of energy in these vertical lines, which you can see here. So there has been one event on one day and the main breakup happened all within one day. And then there's another thing which arises, which you can already see. This touches higher frequencies around, 10 to 20 hertz again. And this is simply the signal of bedload flux. If you see this on the mouse pointer, and if you look closer, you can see that the bedload flux doesn't start after the ice breakup, but that it already has started several days before the ice breakup. 3 to 4 days basically before the ice breaks. So that means already under the ice we had pressurized flow. We had more injection of water into the river system below the ice, which increased the runoff velocity, and that probably mobilized more sediment already before the ice breaks up. So this is one of the new findings already. And if you look at the first part of the spring period, you can also see these diurnal fluxes or these diurnal changes in here. You see these cycles, each of these cycles is a day. And this simply means that during daytime, you have more melting, more injection of water, more bedload transport. And at nighttime, you simply go back to a more stable state. The system refreezes again, and you put less water into the system. And after these 10 days of these 10 days cyclicity, the pattern simply fades out. Why? Because first of all, there's no more snow present. At some point, all the snow is being molten and injected into the river. And the second part is we are in the Arctic here. We are approaching midsummer here. We are 3 weeks away from midsummer. So basically, the nighttime is really short and the daytime is really long. And you simply lose this effect of the diurnal forcing at the later stages of spring. Okay. But now let's look at the seismic inversion of that, right? That was the whole purpose of the entire thing. Again, the black lines is what we have scaled or for what we have independent information, or at least estimates. And you can see that the water level is depicted kind of well. At least the onset of the spring flood is being depicted well. The blue line I'm speaking about now, and also the maximum water level and also the receding phase. What is not depicted so well is the water level at the frozen time or at the ice covered time. Why? We overestimate that simply because we haven't accounted in the model for the turbulence which is being generated at the underside of the ice. Yeah. So usually the model takes into account the riverbed and the river banks, but not any confined surface on top. So this would have been needed to add to the model to fully account for this condition as well. It gets even more interesting if you look at the bed load flux. Yeah. So if you would estimate with typical methods the bed load flux, it would show a strong relationship to water level. But instead, we can see that the bed load flux shows a completely different picture, right? You can see these diurnal fluxes in there in some way, but you will see that the relationship is well, dramatically different. You simply increase, and then after the peak discharge, you still maintain this high level of bed load flux. So the system drains out of sediment more or less independent of the forcing conditions of runoff. And the next interesting thing that you can do is simply, if you do that for the entire time of the year, for example, we just did this for the spring period, obviously, but if you do that continuously, this allows you to look at the erosion rate. Yeah, you simply have the catchment area, and you know how much sediment is going through this measurement site, and this can be converted into catchment-based erosion rates or specific erosion rates. And in the end, this was about 65 tons of sediment that's being flushed out for the entire year, if we assume that most of the sediment is being flushed out at the springtime. Okay, this was the part about the simple fluvial system, right? The simple fluvial system, in a way speaking, we just have a channel which carries water and which episodically also carries sediment. Now we can look for the second part, or that will be a shorter part actually. We can look at less simple systems, at really catastrophically failing systems, and at cascades of hazards. With this, I would take you to India, to the Uttarakhand region, where we had this magnificent and really dangerous hazard in the 7th of February, which I assume you're quite well familiar with. We know quite a bit about this. We know about a bit about this, especially about the violence of the flood that is being triggered from video imagery, which has been recorded and uploaded by people. And you can already see the violence of that flood, right? I mean, we're speaking about a channel that's more than 50 meters wide, a flood that probably reached more than 10 meters depth. And you can see all the dust and steam that is being pushed up into the air simply by this one event. And where do we get all the information from? Basically, we get the information typically from remotely sensed imagery being taken before and being taken after the event. And in this specific case, there was even satellite imagery being taken right as the event happened. So what do we know? We know this entire sequence of hazards started as a rock slide at almost 5 kilometers elevation, or around 4.3 kilometers elevation, dropped down for more than a kilometer as a rock slide, hit the Randigat river system, and basically rushed through this little side valley until it hit the confluence with the Rishiganga river system, and then turned from this massively, really fast traveling, I would call it something. We basically don't even know what the geomorphic term for that is. It's not just a debris flow, and it's no longer a rock slide. It's something in between. Yeah. But it must have been a really, really weird system that happened over there. And after reaching the confluence, it basically traveled down as a massively sediment-laden flood, which then traveled for tens of kilometers down the system. What do people usually do? They collect forensic evidence after the event, basically by comparing information imagery from before the event happened. So this is the power plant that has been hit before the event, and this is what the entire system looked like afterwards. You can see most of the infrastructure is being buried underneath of sediment deposits, and you can also see how these sediment deposits, these gray colors over here, how they basically line the entire channel. And again, yeah, you can see the scale. We are speaking about huge amounts of sediment and huge amounts of areas that have been hit by this event. Something else which you can see is also by forensic evidence, looking at before and after, is where the rock slide has been released. And you can see this. This is the state before, this is the state after, and it allows you to back calculate some volumes that have been detached. And basically, you also get some information on possibly the triggering conditions, or at least on when the event happened, because you see this horizontal or this linear feature over here, which has been treated as a large crack that's being developed and that basically led to the release of this rock avalanche. And obviously, you can also make some estimates or some interpretation of the weather conditions based on satellite imagery and other models that have been based on these satellite imagery, remotely sensed data, I should say. It's not just satellite imagery. And that gives you some information that just a couple of days before you had a lot of precipitation and the warming in this area. So the interpretation would be, this is probably something that has been driven by precipitation. Yeah, but that's all the information that you can get, basically. Now, if you look at what seismic instruments could do, first of all, as I said, you can use for really large scale events, like for this rock slide that in the end released about 23 million cubic meters of rock. Yeah, this generates a lot of seismic energy. You could sense that almost at a global scale. And so you can use the existing network. But if you want to look at the finer details, at the processes that generate less energy, but that are nonetheless also hazardous, you need a really dense network. And luckily, in this case, we had a really dense network thanks to the people from CSIR from India. So that's a station network of almost 80 at the moment. And I will just pick out a couple of them just for locating. So the black star indicates the rock slide, and the blue line basically indicates the propagation path of the flood. And I will basically focus on this one station shown here in this major bend of the river, the Auli station, and then 3 other stations grading away linearly to simply check how far away can you actually sense this seismic signature. Now let's look at the spectrogram. Again, x-axis is time, y-axis is amplitude or velocity of the ground shaking. You can see before the event starts, you just had more or less calm conditions, and then you see this huge and sudden impact of the seismogram, which is actually the release and the impact of the rock slide, indicated here as a yellow star. And then as it fades away into this period of depicted by the green star, which is this massive fast traveling something, we could call it debris flow or valley confined flow, which simply rushed down the little contributing valley, which is this part of the seismogram. And you can see these individual bumps in there, which most likely are bumps when this event hit little bends in the valley course. And then this system basically fades away into phase number 3, which is the sediment-laden flood that propagated for many hours downstream. And you can see that this basically means it's a moderate amplitude of seismic energy. And then as the seismic source travels, I can actually show that over here, as the seismic source travels from the confluence towards the green point, towards the green station, you can see how the amplitude goes up. Yeah. So that's why you also need these close stations. This is basically a mobile seismic source traveling towards the instrument and then passing it and carrying on traveling. Similar to the person that walked along the GFZ campus with the little steps which I showed. Let's look at the events a little bit more in detail. So the really close station was able to basically sense, this is again a spectrogram, to sense the individual signal of the detachment part. And then it took almost a minute, right, for this rock mass, for these 23 million cubic meters of rock to accelerate, to propagate down more than a kilometer of slope, and then generate this massive impact signal. Yeah, so you can actually take the time it takes from detachment to the impact, and convert this into velocity if you want. You can also use the seismic data to infer something which is called the force history, and that gives you some information about the change of forces that are applied to the Earth's surface. If you detach 23 million cubic meters of rock instantaneously, you take away the load of this from the Earth's surface, and the Earth's surface will move back. And this backward move is something which generates a seismic signal, and this can be inverted in terms of forces. So what do we have? The detachment basically generated a force of 10 to the 10 Newton, so that's 11 giganewton, literally speaking, 11 giganewton of force, which simply looks in towards the towards the northwest. So that's basically the back slope going into the opposite direction of the actual rock slide. And then you can also do this for the impact. You can see this here. The impact generated basically 44 giganewton. What does that mean? Basically, you convert a lot of the potential energy after detachment into impact, but you do not convert everything into impact, or not everything into kinetic energy. You also consume some energy simply to break down this massive rock. So a lot of the energy also gets wasted or gets invested in breaking down rock. And you can quantify that from these data. As I said, it was quite easy to detect this first phase, the rock slide, also at more than 600 kilometers away in Kathmandu, or even more than 1,000 kilometers away in Kabul. If you find more quiet stations, you could even sense that further away. The problem is that this low frequency signal also interacted with another event. So this is an earthquake that happened at a completely different site. But you see the contamination of the rock slide signal by the earthquake signals. And again, this is another challenge and another issue with the seismic approach. You sense a lot of different sources, and you have to pick out the ones that really are due to your research area. Okay, so the bottom line is you can basically invert the seismic signal of close stations for the forces that are being at action, and you can use this to quantify what actually happens to the rock. What else can we do? I said we can locate signals, or we can locate sources, and this gets especially interesting for mobile sources, because we can do that location estimate through time, and this is what we did basically. Again, the yellow star is the detachment area of the rock slide, and then we did the location estimate 2 minutes later, which is just basically hitting the valley floor. Again, 2 minutes later, the system had traveled for some 100 meters down slope. Another minute, it made it to there. Then you have this big bend in the side valley, another 3 minutes later. And then it, as I said, it reached the confluence around at 5:02 UTC time. So not local time. That was about 10:22 roughly local time. And you can see how nicely this matches up. We have an aerial image or satellite image, which has been taken around 5.2. And that says the flood has been there by 5.2. And our estimate is just, about 50 meters away, roughly, or about 100 meters away. And then you can see that you can follow the propagation of this flood all the way the main valley. So what we can do is we can locate and track such a linearly propagating chain of hazardous processes. And once you have the location and the timing, you can also convert this into velocity, as I said. And so you can see that the rock slide really, really was moving fast. So we're speaking about velocities of 50 meters per second. Or more than 160 kilometers per hour. So this is a really fast traveling train of rock and water and ice. And then as it moved down the slope or down the channel, it lost velocity, but then in the end, you're still around 20 meters per second. So that's a train moving at about 60 to 70 to 80 kilometers per hour. So you don't want to get hit by that as well. And then you can basically do that all along the stream. I should say that this particular point is an artifact which is due to the really coarse location estimate over here. So this shouldn't be interpreted in this way. Basically, you start with a really fast rock avalanche, a really fast valley confined flow into the main valley, and then you have this flood propagating with about 15, 10, 20 meters per second as it goes down. Last question, and then I'm done and open for questions. How far away can you actually sense this part? As I said, I just simply moved back. there have been three phases, right? There has been this magnificent rock slide, which, as I said, generated a seismic wave, which traveled for thousands of kilometers and which can be easily sensed by existing systems. This graded into the debris flow, which delivered way less energy, way less seismic energy. And then it turned into this flood, and the flood did most of the hazard, right? Because it carried large amounts of water, it propagated through populated places, and it hit one hydropower project after another. But this is the one that really has the least seismic energy being delivered. So you need a close network for that. And for this, we look at the other stations. This is a station only 38 kilometers away. And you can see this is the orange part is still the seismic signature of the rock slide and the debris flow that it spawned and triggered. And then this is basically, I shaded this in the white polygon over here. This is the imprint of the flood part. So you could sense it at 38 kilometers away. You can also sense it at 50 kilometers away. You can see this really, really tiny horizontal line. It gets more clear if you look at the spectrogram in a different way, but I simply wanted them all on the same scale over here. And then at about 59 kilometers, you don't see any of that signal anymore. So it's not recorded by this third station. Why? I mean, it's just another 8 kilometers away, right? But the problem is all of this is also due to how the station is coupled to the ground and how much environmental noise you have around your station. Yeah, environmental noise could be factories, machineries, road traffic, people living, walking, playing. That could be rain, that could be wind. There could be a lot of different seismic sources that overprint your signal so that you simply can't see it anymore. As an advice for future deployments, if we are really interested in looking at seismic detection and tracking of such events, you really need a close-based network, and you have to pay due attention to where you actually deploy your stations. And this is basically it. I think I just leave you with this gaping peak in the Alps, where I will be going in a couple of days. And I would skip all the take-home messages because I think that's a bit ridiculous after 60 minutes of rushing through environmental seismology concepts, methods, and 2 applications. And I would simply take questions if you want to. Otherwise, thank you.